Hello, and welcome to Lecture 4 of Kinematics in 2D. And here we're just going to have a very short introduction to uniform circular motion. We have a whole unit of the course later on that'll look at uniform circular motion. So we're just going to connect some of the ideas we've been looking at in 2D motion with uniform circular motion. And we will come back and deal with uniform circular motion more fully after we've dealt with forces. And I'll just say what I mean by uniform circular motion is circular motion at constant speed. And notice that's constant speed, not constant velocity. We need to talk about that. Back in the vectors unit, we've already seen what happens when something is going around a corner at constant speed, but this is the sort of thing where the more times you see it, the better. So here's the motion diagram for an object going in a circle at constant speed, right? So this is what we call uniform circular motion. And let's just do the vector subtraction to find the direction of the acceleration. So I'm going to choose this point, and so this is my VF, and I'm going to pull it out over here. And this is my VI. So I'm going to pull it out over here, and I need to flip my VI as usual so that I can do a vector subtraction. And I'm going to bring it up here, and I'm just going to cheat by using all the capabilities of the program I'm in and snug those up. And there you see that delta V is that way. And so that says that the acceleration at that point is directly into the center, right? So I can grab that and stick it there. And if you repeat this analysis everywhere else, you're going to find that the acceleration is into the center at every point here. So we've just seen how to show that the acceleration points straight in. Also, because these speeds are constant all the way around, all of those vector subtractions result in the same magnitude of the acceleration. So now we have to be very careful about some terminology. The magnitude of the velocity, okay, and the magnitude of an instantaneous velocity is just the speed, that's constant. But the velocity itself is not constant. Look, it's changing direction. The velocity vector is changing, even though the speed is constant. And remember, changing the direction of the velocity vector is accelerating. So we have an acceleration, and its magnitude is also constant. But the acceleration vector is not constant because it's changing direction too. So in uniform circular motion, the magnitudes of the velocity and the acceleration are constant, but the velocity and acceleration vectors are not. So I'm just going to summarize the really key points about uniform circular motion. The acceleration, as we just saw, points to the center of the circle. Now, remember, these are average velocity vectors. If you instead look at instantaneous velocity vectors at the same time as these accelerations, you find that the acceleration is always perpendicular to the velocity, right? And this is something that you would know from geometry from years ago in school, I hope, that a line that is radial to a circle and a line that is tangent to the same point will be perpendicular to each other. And then the final thing, which we'll show in a moment, is that the magnitude of the acceleration is v squared over r, where v is just the speed, and remember, it's uniform, and r is the radius of the circle. This isn't a course where I think you should worry about being able to do these derivations, and so most of the time I won't even show derivations like this, but this time I think this one's worth seeing. Don't feel that you need to be able to reproduce this derivation. I just want you to see some of these arguments. A equals v squared over r, right? And this is a magnitude, and that's a speed, also a magnitude. And let's get this. So here's the circle. And we have some object going around, and there's its displacement vector for some small time interval, and a VI and a VF. And one thing to notice is that there are actually two triangles we can construct here, and they turn out to be similar. If you take the VF minus VI, we've seen that plenty of times, right? So here's VF minus VI, and so this gives us a delta V. And hopefully you can see where this is going, sort of, because delta V is our way of getting to A, right? So there's VF and minus VI. And the crucial thing to notice is that this angle in here is theta, the same angle as is in here. And that means these two triangles are similar. And whenever you have similar triangles, then ratios of side lengths are the same. So in particular, this means that delta V, I'm not going to put a vector on it, right? I'm saying the magnitude of delta V over the magnitude of either of these, but that's the same. That's just V, the speed, right? Uniform circular motion is equal to, and then again, it's going to be the magnitude delta X over R. There's the similar triangles. Now, there's an argument we need to make now, and it's actually slightly wrong. And I'll come back and tell you how to fix it, but for now we can't really fix it. So I'm going to say this delta X is V delta T. Okay, that's the speed, this is time, here's how far it goes. Now, I've just made a mistake. It's not a serious mistake, but that's wrong. But let's go ahead, we'll put that in here. So delta V over V equals V delta T over R. And if you just rearrange that a little bit, you get that delta V over delta T is V squared over R. And again, making a very similar mistake, I'm going to claim that that is A. Okay, now technically that's not correct. A vector is delta V vector over delta T. Okay, but this isn't quite correct. But it ends up being fixed by the same thing that we do to fix this. So first realize why this is wrong. V delta T is the distance traveled. It's not the magnitude of the displacement, and the distance traveled is the length of this little arc here, whereas delta X is the length of this straight line. So in fact, those aren't quite equal. The thing is, if you make theta very small, then they become very close together. And in the limit, the theta gets infinitely small. They're the same. And this all works out. And it turns out that also fixes the problem down here. But this is a non-calculus physics course, and going through that argument properly involves some calculus. So a good example from sports of uniform circular motion is short track speed skating. When they're going around the curves in short track speed skating, they really are going around something very close to a portion of a circle, and they're going at very nearly uniform speed. And so the acceleration should point straight into the middle of the circle, and the velocity is tangent to it. And because of the perspective, it doesn't look like those are perpendicular in this picture, but they are. So in the women's 1,000-meter short track speed skate, the current Olympic record is due to Valérie Martin, and it is 1:28.771. And so from that we can get her average speed. It's around then 1,000 meters divided by 89 seconds. Remember, this is an average speed. We don't care about any directions here. And that comes out to a little over 11 meters per second. Now also, the shape of the track, there are these semicircles at the ends. And just what radius they're going around, of course, depends on how closely they hug the inside of the curve, but they try and get pretty close to the inside, and that's around about 11 meters. So we can now estimate her acceleration as she goes around the corners. So remember, I'm not putting a vector symbol on this because this is a magnitude of an acceleration, and it's going to be v squared over r, where that v there is the speed. And so that's pretty much 11 meters per second squared over 11 meters. Okay, note meters squared. This is all going to come out in meters per second squared, and 11 squared divided by 11 is 11. So, I mean, the thing that's impressive about that is that that is somewhat larger than acceleration due to gravity, which you could never manage off ice without skates because you just don't have the traction, but with the blades biting into the ice, you can manage accelerations higher than g. So just to summarize this whole unit, I want to compare and contrast these two very important special cases, projectile motion and uniform circular motion. And as we've seen, in projectile motion, the acceleration is constant, absolutely constant. Everything about it, its magnitude and its direction, are both constant. But the speed and the velocity constantly change. The velocity's direction is changing, and its magnitude is also changing. In uniform circular motion, the magnitudes of both the acceleration and velocity are constant, but both the acceleration and velocity are constantly changing direction. And another thing is that in uniform circular motion, the velocity and acceleration are always at right angles to each other, whereas in projectile motion, the angle between them is changing all the time.